Hi guys, we're ready to do 4.3. I hope that you have practiced doing the integrals from 4.1 and then you've got the hang of the power rule integration where you're just going backwards. Instead of multiplying and subtracting, you're going to add and divide. I put a box up there for the homework and now I can't reach it with this screen, so let me fix this. The homework for 4.3 is going to be 5 through 13, 25 through 31. I changed it a little bit from what's on Canvas, and I don't know that I'm going to remember to fix Canvas, so I'm telling you now. And 55 odd. Most of these, there's not a whole lot of work involved because you're given the function, you can assume that it's positive. And if it's not always positive, they don't want you to worry about it anyway. So you'll understand what I mean when we get to it. Now, we are skipping 4.2 in case you didn't notice. It's developing the definition of what an integral is. We're going to be using that definition instead of doing the grunt work of figuring it out. And what you see at the bottom of page 400 under definition there is that the integral from a to b of some function is actually a limit, as that's a delta. It's kind of like the dx that we always talk about. It's a small change in x of this big capital sigma. It's a Greek letter. As I goes from 1 to n, sorry, my other class is doing infinity right now. 1 to n of, now the capital sigma means a great big sum. You're going to just add a whole bunch of terms together. And what this means is, let's say you have a graph and you're going from A to B. And you want to find the area underneath that curve. It's not a rectangle, it's not a triangle, it's not a circle. So how are you going to find the area there? Well, one way to do it is to break it up into pieces. And then you can treat each piece like it's a rectangle. So let's make that like that. You see those rectangles? Now notice that that's not in there, that's out there. It might average out to be pretty good, but what's a way that we can make it even more? By the way, what's the area of a rectangle? It's width times height, right? So let's see if we can make this a little bit more precise. And we're going to cut those in half. Whoops. And now I've got those. You see there's still too much in some places and too little in other places. And the only way to make this perfect is if we have an infinite number of rectangles. If there's an infinite number of rectangles, then the width is a very tiny change in the x value, and the height of each rectangle is the y value for whatever x you're at. So this represents the height, there's your width, and you're going to add them all together to get the area. So what this little exercise does is it shows you that the definition, or what that integral actually represents, is the area, I'm going to use quotes, under f of x between those two x values. Now I say under because that's assuming that the curve is above the x-axis. If the curve dips below the x-axis, let me continue this like that. For this area right here, that area is negative, whereas the area above the x-axis is positive. Now, if you were talking about how much concrete you needed to pour, you would need to add those areas together. But if this curve represents your profits, something like that, you wouldn't want to make this area positive and then flip this up and make this positive as well, right? This would be your losses, this would be your profits, and you would need that negative area to take away from that positive area and find the net value. So that's why we're not going to worry too much about this. For most of the applications that you'll be integrating for, you want negative to be negative. So you're just going to integrate from A to B all of that area underneath the curve. That's positive area, that's negative area. You just do the plain old integral. This is called a definite integral. What you did in the homework didn't have these limits on it. These are x values. What you've done so far didn't have those limits. So you did an indefinite integral. What we'll be doing from now on, or at least in this section, whatever, are definite integrals. Remember that plus c? That was an indefinite value. You didn't know what the c was. But now when we do these, we will not have the plus c because we're going to be plugging in the endpoints of the interval that we're integrating over. I know that's a lot, but it really is pretty basic. So let's get going. So if you have a definite integral from, let's say, 0 to 3 of some function, you're going to do exactly what you did in the last section. You're going to integrate we're going to not have the plus c because we're going to take those x values that were our limits of integration here, and we're going to use this evaluation bar. Once we've done the integrals, this stuff here, added 1 to the power and divided by the power, we no longer have the integral symbol. We have done this work. What's left is to evaluate that from 0 to 3. So, always and forever, amen, simplify before you start plugging in values. And always and forever, amen, from this point on, everything is always going to be top minus bottom. If you remember that, no matter what you're doing, you'll always do the right thing, top minus the bottom. So when we evaluate the integral, we're going to take the top number, 3, and plug that in. This is the top. Minus, plug in the bottom. Top minus the bottom every time. So take 3, plug it in. I got 3 cubed over 3. Plus 2 times 3 squared. Minus 2 times 3. And then we plug in the bottom number. Plug in 0 for all of those x's, and we get 0. Love the zeros. So here we have a 9 plus an 18 minus a 6. That's going to give me 21. And 21 represents the area between that curve and the x-axis between the x values of 0 and 3. Now let's do a real area problem. Let's see, a lot of the problems in your homework have the graph. Let's look at this guy right here. This is 4 minus x squared. First thing we want to find is that area right there. So we're going to integrate from 0 to x equals 2. The function is above the x-axis, so we just integrate and then plug in the numbers. So we have 4 times 2 minus 2 cubed over 3 minus, plug in the 0. So 8 minus 8 thirds, common denominator is 3. 8 times 3 is 24. And we get 16 thirds. Make sense? All right. Now let's do something a little different now. Let's take that same function. It crosses here at 2. It's up here at 4. But let's go all the way to 3. Now, if I'm finding area, I see that this part from 0 to 2 is above the x-axis, but this part is below. So this area is negative. Remember, I told you top minus bottom. That goes for setting up your integral as well. For from 0 to 2, the top, let's look at one of our little rectangles. Remember, we've split it up into an infinite number of rectangles. We've got a rectangle right there. So let's look at the red rectangle. What's the top of that? The top is the curve. Now, this rectangle could be anywhere from x equals 0 all the way to x equals 2. The rectangle is moving, and the height of the rectangle is changing. It's variable, and the height of it is just the top minus the bottom. So it's going to be our function minus, what does y equal here? 0. So the top minus the bottom will be, for that first part, the integral from 0 to 2, the top is 4 minus x squared. The bottom is 0, so I'm going to say minus 0. I'm integrating with respect to x. Then I want to add the area that's blue. So I'm going to add from 2 to 3. What's the top? What's the y value here? 0. What's the y value of the bottom? The curve. So what I'm integrating here is 0 minus the curve itself. Top minus bottom always. But if I have 0 minus something, isn't that just the negative of it? So what we're going to do is, instead of doing it that way, we're just going to make this negative. So because the area, because the area is negative, so the value of this integral would be negative, and we're subtracting it. So minus a negative is a positive. So let's just get her done. We're going to integrate. And evaluate. Minus, integrate, and evaluate. Whoops, I made a mistake. Did you catch it? This first integral stops at 2. So we're going to plug in the top minus the bottom for the first thing. Minus, plug in the top minus the bottom for the second. So I plug in a 2, I get 8 minus 8/3, just like before. Plug in the 0, I get a 0. Now in the second one, I'm going to plug in a 3. That gives me 12 minus 3 cubed divided by 3 is 9. Minus, plug in the 2, 8 minus 8/3. Wait a second. I've got 8 minus 8/3 here, and minus 8 minus 8/3 here. So are they going to cancel? No. Minus a negative is plus. It actually doubles. Okay? Now, when you evaluate these integrals, you're going to get lots of fractions, and you're just going to have to grit your teeth and decide that you love it, right? All right, so we have 8 minus 8/3 minus 0, and then that's in the first thing. In the second thing, 12 minus 9 is 3, minus, I'm going to distribute that minus back here. I get, I get minus 8 plus 8/3 because it's minus a negative. So 8 minus 8/3 minus a negative, 3 minus 8 is 5, and then minus 8/3. So put your whole numbers together, put your fractions together. Common denominator, I got 39, I'm running out of room, minus 16 all over 3. 39 minus 16 is 23 over 3. Okay? Now, that was the area. What if I wanted to just find the net? In other words, just do the definite integral. For this guy right here. In this case, if we just integrate from 0 to 3, 4 minus x squared, we're doing this to see what difference it makes. 4x minus x cubed over 3, are you sick of that yet? From 0 to 3. When we plug in the 0, it's 0, so all we have to do is plug in the 3. 12 minus 9 equals 6. Now look at the difference between the 6 and the 23/3. 23/3 is 7 2/3, so it's bigger, right? That's the difference between adding that area and getting this answer and subtracting this area from this area and getting a 6. Okay? So there you've got some examples of actual area problems and just finding the definite integral. And
okay, now for the fundamental theorem of calculus. And let's spell fundamental correctly. Fundamental theorem of calculus. It's not as bad as it sounds. It's just what you just did with the area. So this is the infinite sum, because n is going to infinity, of the y values for each of the x values from a to b, remember, and we chopped it up so that that's an infinite amount. Delta x is the width of each of the rectangles. You're plugging in each of the x values into the f to get the height of each of the rectangles. And remember, the sigma gives you the infinite sum. So your integral is actually defined as this infinite sum of height times width. And when you do this, f of x is the derivative of some function capital F. So you undo the derivative and you just plug in the top number minus the bottom number. And that is the fundamental theorem of calculus. Integrate the function, which is the derivative of the capital F, and then you plug in the top number minus the bottom number, and that gives you the area. And that's it. Please remember, guys, don't let yourselves get overwhelmed. Don't let yourselves get behind. We have a lot of material to cover, and it's just an 8-week semester. It is MAF 3.5, not 3.3. Sorry. If you haven't connected with me on Hangouts yet, I'm always there to answer your questions. You can, if you're struggling with a homework problem, you can snap a picture and text it to me right in that app, and I can do the same back to you if you don't want to get on Zoom. If you do want to get on Zoom, text me and let me know that you need me, and we'll set up a time if we can't do it right then. And remember, I don't have to see you on Zoom. You're not going to see me most of the time. I'll just use my whiteboard, and then I can't see you anyway. So take advantage of my help, please. We're halfway there, a little past halfway there, but it gets harder, not easier. So make sure that you contact me whenever you need me. All right?